Okay, so we will continue. So last class actually we were discussing about maybe the how to define the discriminant function. Okay, the defining decision regions, the decision boundary, etc. Okay, and then we have seen the various maybe the how we can actually maybe so define the classifier for multi-category, okay, etc. So now what we will discuss is so we have seen that the probability density function. Okay, so for example, if it is a continuous variable, okay, we have actually a probability, okay, something like a probability of x given wi, okay, maybe on the as a likelihood function actually in the base decision okay theory. So now we will quickly go through what is the maybe the most commonly used okay maybe density function, okay, standard density functions which can be maybe used for our analysis. Okay, how we can actually assume that okay maybe okay say this particular probability can be okay represented by okay this standard okay probability distribution. So that is our aim. And so we know that the normal density function or the Gaussian density, okay, say that is actually a very standard, okay, or very commonly maybe I mean maybe representation that can be approximated, okay, or we can actually approximate many probability distributions okay into a normal okay density curve or the Gaussian density curve. And we have actually started with the curve fitting problem, okay, by generating maybe a few samples actually, okay, from maybe the sine wave, okay, which is actually a standard curve, and by adding some random noises, okay. So the same way we can assume that the features that we will be maybe coming across, okay, in various maybe say problems in machine learning or pattern recognition, we can assume that they are also maybe generated by the probability distribution, which is a normal distribution, but there was actually maybe say some noises maybe or say random okay variations happened, okay, as we have actually seen with the curve fitting. So we can say that the continuous variables that we will be using, okay, in our pattern recognition can be better approximated to a normal density. Okay, but if you are actually specifically know that okay this particular maybe feature is actually well represented maybe some other distribution, maybe so that the whatever analysis that we maybe we will be going through can easily be extended to that particular say distribution also, okay. But this is actually a very commonly occurring, okay, and maybe the best approximation that we can actually always make it. And it has got a lot of advantages if we are actually assuming that the continuous random variables that we are actually okay coming across in this, or we are actually dealing are actually maybe are following okay a normal distribution. So that is why we will be discussing specifically on two types. One is actually a univariate density, so that means we are having only a single variable, that means a single feature, because we have actually seen so far our discussions in two steps. So that means phase one or in step one, we always with a single feature, okay, and then we extend that to maybe multiple features or say into a multi-dimensional. So similarly, here we'll be seeing what is going to be a univariate, okay, and what is going to be maybe multivariate. So first we will see how the probability densities can be represented using probability distributions of say normal okay density. And when you consider the normal density, okay, so we as I mentioned this, and there are a lot of advantages because it is one of the most widely analyzed, okay, and maybe easy to maybe analyze or tractable, okay. So there are a lot of advantages if we assume that the density is actually normal density. So densities which is analytically tractable, okay, so that is actually one advantage. And it is a continuous density, okay, so we are also assuming that our variables are actually maybe continuous, okay. and then we can say that a lot of processes are maybe assuming as a Gaussian. Okay, so that means many real maybe say processes, okay, real world process, we can assume that they follow a Gaussian, okay, way. So there are a lot of such maybe reasons why this is actually the best way to start with the discussion. So, for example, we can say that a handwritten characters, speech sounds, okay, or anything, okay. So, of those sort we will come across are actually a prototype, okay, which are corrupted by some random processes. Okay, so that is the way that we discussed with the curve fitting example. Similarly, that can be extended to or applicable to maybe say other cases also. Okay, so we can say that there is a particular character, okay, and all other maybe characters that are written by various people are actually corruptions, maybe due to some maybe due to many reasons. Okay, so that's why the way we can actually approximate that. Okay, so this is actually called a central limit theorem. So we are actually not going to the details of such mathematics, but that is a way why we are actually discussing this one. Okay, and this is actually the equation, okay, maybe for a normal density. I think you some of you might have already seen, okay, that particular equation, so which is actually 1 by square root of 2 pi sigma exp of say minus 1 by 2 x minus mu by sigma the whole square. So this is a univariate, okay, density function. Okay, so here we are assuming that x is a single variable. Okay, and we know that if you look into the normal density say curve, which is a bell-shaped curve, okay, so this particular probability is actually well defined by maybe two parameters. So one is actually we know that the this mu, and another one is actually the sigma. Okay, and x is actually the given feature. Okay, so that means we can say that mu is actually nothing but the average value or the mean vector, okay, or the expected value of x. Okay, so that is a one parameter, and sigma square is actually the expected square deviation, or we call it as variance. Okay, so the mean value, mu, and the variance are the two parameters actually that determine the maybe the orientation or the distribution of this particular maybe probability. So this is a very fundamental equation. Okay, I think there is no need of much other details on this one. Okay, and so that means we have actually an univariate density, okay, that we have a just C. Okay, and as we know that this is a probability value, so we can it is a function. Okay, so we can say that what is going to be the expected value of x. Okay, so which is actually average over the feature space. Okay, so we can define the expected value. We have already seen how we can actually define the expected value or the average value. Okay, we have already seen. So that is the expected value of x is nothing but a minus infinity to plus infinity x into, okay, p of x into dx. Okay, so that is the way we can actually maybe define the expected value. Similarly, the variance, okay, so that can also be defined, which is nothing but the expected value of x minus mu the whole square. Okay, so that is a square deviation. Okay, so that is minus infinity to plus infinity x minus mu the whole square into px dx. So that is a what two maybe things that we can define. Okay, and now we will see in multivariate we will see. Okay, but we will discuss that in detail. But we know that that is going to be in d dimension. Okay, so the equation is going to be, okay, we can say that instead of maybe a single feature, we will have the feature vector x, okay, which is of maybe a three dimension. Okay, so in d dimension. Okay, so before going into that particular thing, so let us say that this is a maybe a standard plot of a univariate normal distribution. Okay, and so so if you look into this particular plot, okay, we can say that majority of the points, okay, so 95 percentage, okay, of these points are actually falling in the range of x minus mu and x plus mu. Okay, so that is x minus mu less than or equal to 2 sigma. Okay, so that is why the this sigma and a minus sigma. So that is a, can say that a 95 percentage of the points are actually falling in that particular range. Okay, and we can say that if you consider, okay, mu plus 2 sigma and mu minus 2 sigma, okay, so that region will accommodate around say more than, or say near to 95, okay, percentage, and we are having only very small points actually falling in this particular, say, range. Okay, so that is actually the interesting, okay, maybe one property of this particular plot. And so if you look into this peak of this particular distribution, so where we know that the x actually takes the value of mu, okay, because mu is actually the I mean the mean value, okay, or the average value. And so if you substitute, we have x is equal to mu in this equation, okay, x is equal to mu, because when x takes the mean value, so this term will, okay, become 1. And we know that so we'll have the peak value, or the peak of the distribution has a value of 1 by okay, a square root of 2 pi sigma. So that means we'll have only this particular term, say, remaining. So that is actually the peak value, okay, is determined by substituting x is equal to mu. Okay, so this is actually the maybe how this curve will look like. uh, okay, so that is one point. And so when we consider a multivariate normal density, so that means we know that so we know that we have to replace, okay, small x by capital X. Okay, so that is okay. Okay. So we have to replace actually single feature with the feature vector. But here, yeah, as earlier we have actually considered one feature, and we will calculate maybe that feature value and its mean value we can easily calculate it. But when you are having a table that we have seen, okay, in the last classes, that means we are having maybe feature 1, feature 2, etc., up to say n number of features. Okay, so it is not a single, for each of the features we can actually have a mean vector, sorry, a mean value. Okay, so that means we have a feature vector, similarly we can have a mean vector also. Okay, so that is one thing. And when you have the variance, so variance is actually we are actually defining a feature with respect to its mean value. So but when it comes to so the multivariate case, okay, we have to consider, okay, maybe say for example the variance, say how maybe two features are actually varying together. Okay, so that we can actually maybe or maybe we have to consider all such okay possibilities. Okay, so considering that particular points, okay, so suppose the general equation for a multivariate normal density in d dimension is, this is the equation. Okay, so we are not going to the proof of maybe how these are derived. That is maybe if you are interested, you can go and study the probability, okay, maybe derivations and all those things, but that is not our maybe prime importance. But this is the equation, because we have to see maybe how we can represent, suppose we are representing with the normal density, okay, as a probability distribution. So then maybe how we can actually make use of maybe a decision making, okay, using this particular maybe probability say distribution. That is our interest. Anyway, so the equation will become it is similar to the previous one, but because some of the terms we have to consider separately. So that means it is 1 by, instead of square root of 2 pi, we have okay, 2 pi raised to d by 2. So you can see that the number of dimension, okay, is coming into uh, here. And sigma, okay, this is earlier we have only a variance, so that means that we have only one feature. But here now we have to consider multiple variables and their variances. So that means there is a sigma is actually we call it as a covariance matrix. Okay, so that is a sigma here. Okay, but we can say that concept wise this is going to be in same line with the univariate. So that is a and so sigma is actually a covariance matrix. So we have a modulus of sigma is going to be it's a determinant. Okay, so because in matrix maybe in linear algebra, okay, modulus of a matrix actually represents its determinant. Okay, fine. Then exp of minus half into, okay, So earlier we have x minus mu by sigma the whole square, but now slightly it is modified. So, but conceptually it is same, that is x minus mu the whole transpose. Okay, this t represents the transpose of maybe the difference in the I mean the feature vector and the mean vector. Okay, and sigma inverse. So here comes the maybe the inverse of the mean covariance matrix multiplied by x minus mu. So this is a here also we can say that if you look into this one, this also almost represents x minus mu the whole square by sigma. Okay, the whole square, but as we have to extend this to a feature space in d-dimensional, we have to maybe have this representation. Okay, so that is a multivariate normal density. Okay, and so suppose here we can say that the probability we are actually approximating to a normal distribution. So in that way, how we can represent it is actually this n represents okay normal density, and they are actually described by two parameters mu and sigma. So in the univariate case we can write it is like a maybe mu comma sigma. Okay, so that means but here we have the covariance matrix we have to consider. So that is a way how we are we can maybe approximate this probability and corresponding density. Okay, probability density. So we can say that x is equal to the okay, they are actually the feature vector. Okay, where t stands for the transpose. Okay, then mu is actually going to be the mean vector corresponding to each of the features, and this is a covariance matrix. Okay, and modulus of sigma is actually the determinant. Okay, and the sigma inverse raised to minus 1 is actually the inverse. So this is actually the general equation, okay, for a multivariate normal density in d-dimensional. So that means here also we can actually define maybe the expected value of x. Okay, because that is a mu value. But here you have to consider the entire vector or the entire feature space. Okay, and similarly we can define the covariance matrix. Okay, so that is nothing but the expected value of x minus mu into x minus mu. Okay, transpose. So that is a the difference. Okay, in notation that comes, and that is nothing but okay, x minus mu into x minus mu transpose into px into dx is going to be in the entire feature space. So that is actually maybe the how we can actually define the average value and the covariance. Okay, in the case of a d-dimensional but say multivariate case. So that is one thing, and so we have a okay. So if you look into this previous equation, okay, so we can say that that previous equation is completely determined by okay, we have a d component mean vector. Okay, so that means d parameters. Along with it, we have a okay the independent elements. That means the off diagonal elements of a covariance matrix. So covariance matrix is going to be with respect to d by d. Okay, it is d cross d matrix. Okay, so d cross d matrix, and so that means we'll have a x1 to xd, okay, along in this direction and in this direction. So that is it's going to be the covariance of x1 with respect to x1, x1 with respect to x2, x1 with respect to x3, etc. up to d. So similarly we'll have a matrix. Okay, and so that means we may have actually but d into d plus 1 by 2. Okay, parameters okay, coming from the covariance matrix also. So the total we have a d plus d into d plus 1 by 2. Okay, parameters are going to determine maybe, or that is determining the entire maybe the multivariate normal density. Okay, and so that is another point. We'll come to this later. Okay, so that is how we can actually extend to n d dimension. And there are many properties. Okay, if you are considering maybe the normal density covariance matrix, because if you look into this particular equation, the crucial thing that is going to determine okay different cases of this multivariate normal density is going to be the covariance matrix. Okay, Okay, because others are actually nothing but x the mean vector and its difference, but the covariance matrix will determine maybe how these features are actually maybe covariing, okay, together, and that can have a lot of impact actually on this particular probability value. So okay, so but again, we are not going to the detailed analysis of such things, but keep in mind that we know that it is going to be symmetric, because it is going to be d cross d, because the same features are actually on the row and column of the matrix. Okay, and so there is some properties we are assuming that with respect to this pattern recognition analysis, we assume that this covariance matrix okay, will have a few properties satisfied. So one such property is actually positive, okay, definite value. Okay, so which means that the determinant is say positive. So that is actually another condition that must be satisfied by this covariance matrix. So that is we are not going to the details of what is this positive definitive, okay, positive semi definitive. There are many such maybe properties. Okay, but one thing is actually in our purpose, we are assuming that it is actually positive definitive. Okay, so that means the means determinant is actually positive. Okay, and it is interesting that okay, another property which also not that significant maybe in our analysis is suppose we can actually always okay maybe look at maybe how the points will be falling on. Okay, if you plot actually, okay, so for example you have x1 and x2, okay, along x and y directions. Okay, how the points will look like, how this feature space, this probability value will be, the points will be distributed. Okay, so that is again that aspects okay is not going to affect maybe in our pattern decision making, but just to have a quick idea. Okay, we will go through that one. So suppose we can actually you might have know about maybe eigenvalues and eigenvectors, okay, of a matrix. Okay, so here we can actually consider the covariance matrix, and then you can actually find out the eigenvalues and the eigenvectors of this particular say covariance matrix, and using that particular okay maybe eigenvectors and eigenvalues, okay, we can actually maybe plot, okay, maybe how the points are actually falling. Okay, so that is interesting thing is actually so if you sample, okay, suppose drawn from a normal population. Okay, suppose you sample the points, okay, from a normal distribution curve. Okay, and so that points tends to fall in a single cloud, okay, or cluster. So that is a property that is maintained by normal density. Okay, and so that is actually maybe this particular plot shows. Okay, so this is samples drawn from a two-dimensional Gaussian. Okay, so that means you have a two variables. Okay, and if you plot, okay, these points with respect to a center point mu. Okay, so here we can there is a mu. Okay, you can see that there is a mu. Okay, labeled here. So that means these points will fall, okay, on a cloud, okay, or a cluster, okay, which is centered actually around the mean vector. Okay, and the ellipses actually shows okay equal probability density. So that is another point. Okay, so the points will fall like this one. So that is just to have an idea. Okay, so that means the center of the that cloud or okay is actually determined by the mean vector, and the shape is actually determined by maybe the covariance matrix. Okay, so that means mainly it will be maybe say ellipse in shape, or we call it as a hyper ellipsoid, maybe in a multi-dimensional case. I think ellipse you might have studied during your geometry classes, and it is usually we talk about two axes. Okay, but if you extend maybe this ellipse into maybe multi-dimensional space, we call it as hyperellipsoid. Okay, so because we are having dealing with the d dimensions, so that means we have to have a hyperellipsoid actually maybe generally that will be coming across. Okay, so anyway, so the center and shape is actually determined by this one. Okay, and if you look into the locus of points, okay, of constant density, and they actually forms a hyperellipsoid. Okay, just to have an idea. Okay, and if you know that there's a principal axis, okay, for the ellipse, okay, major axis and minor axis you might have studied. Okay, so when you consider this hyperellipsoid, as already mentioned, this axis, the directions are actually determined by the eigenvectors, okay, of the covariance matrix, and the magnitude of that axis are actually determined by the eigen maybe values. Okay, again we are not going to the analysis, okay, of that direction. Anyway, that is one point you can keep in mind. If you are interested, you can go and read more on. Okay, and another distance measure that is generally maybe defined along with this analysis is, suppose we have a distance of this kind, that is x minus mu transposed into sigma inverse into x minus mu. So that distance measure, okay, let us represent it as r square. So it is actually called Mahalanobis distance. Okay, this we will will come across maybe later. So it is called Mahalanobis distance from x to mu. So that means x is actually the feature vector, and mu is actually the mean vector. Okay, so the suppose the mean vector is actually we can calculate with respect to the given value, and we can always, suppose they are given a new feature vector, then you can actually find out the distance of the given feature vector x to the mean vector, maybe the mu. So that way we can actually calculate maybe with respect to the mean vector where is the current feature vector actually lies. So that is one interesting measure that is defined in this context. Okay, then so that is actually maybe this particular point. And there are many ways, there are some transformations you can actually apply, and that will result in maybe different forms of maybe this maybe the points falling. Okay, you can convert that the ellipsoid into a circular, okay, things. So we are actually not going to discuss those details, and if it is required maybe in our analysis we will come to this particular point again. So but keep in mind that this is the way how this points are having same probability will be falling. Okay, and how maybe the axis, okay, and the directions are actually determined. Okay, maybe just to I have an overall idea. Okay, and now we will go to our interest is actually okay. Suppose we know that what is a discriminant function we have already defined. Okay, because discriminant function is going to be g of x we have defined. Okay, for a C category problem, and we will consider gi of x for each I, and for which maybe j for which I j of x is actually the largest, then we will assign maybe the class level, okay, that wi, okay, to the given feature vector x. So that is a where we have seen what is the need for a maybe discriminant function. Okay, so how we can actually now make use of, suppose our probability is defined using a multivariate Gaussian density, then how the discriminant function will look like, and how we can have a different cases. Okay, so how can simplify the decision discriminant functions, and maybe see different cases. So this is the equation that we have just seen. That is the normal density of mu and sigma, the equation that we have just seen. Okay, and we have actually seen different ways in which we can represent the discriminant functions, like g of x is equal to, okay, natural logarithm of probability of x given wi plus probability logarithm of say probability of wi. Okay, so that is, we know that here we have, this is going to be a prior probability, okay, which is going to be having no what change with respect to x. Okay, we have already determined it. So now what is here interesting is actually this likelihood function, that is probability of x given wi, and assume that now what we will do is we assume that this probability actually is following a normal distribution. Okay, especially a multivariate normal distribution. So if that is the case, this probability value can be replaced by, we are assuming that this is equal to the normal distribution of mu and covariance matrix. Okay, so that is this particular assumption we are actually making. Then we can substitute this whole equation, Okay, this equation for normal multivariate Gaussian density, we can substitute in this particular equation, okay, and rearrange it. Okay, then we will get maybe this the last equation, that is g of x is equal to minus half x minus mu into, okay, sigma I. That I represents because we are actually defining discriminant function, so that means it can be g1 of x, g2 of x, g3 of x for maybe for different classes w1, w2, w3. Okay, and so for each of the cases we can calculate the covariance matrix, okay, and its inverse, and we can find out this product, and minus d by 2 into ln of 2 pi minus, okay. So this is the except the last term, okay, all the four terms are actually sorry, the three terms are actually coming from substituting this equation, okay, in this particular probability. And the last one we have a natural logarithm of maybe probability, prior probability, okay. So that term is actually kept as such. So this is how we, and we substitute that equation in this our discriminant function, okay. And now we have to see how there are different cases, okay, maybe how we can actually simplify this g of x, and how we can decide, okay, maybe given x, okay, into which class. So there are different cases, okay, especially with respect to the value of maybe sigma, as I already mentioned, okay, as I already mentioned. So suppose we assume that we have a case one. Okay, so the case one is, let us say that sigma I is equal to sigma square. Okay, so that means we assume the into diagonal, that is sigma square I, it is actually, okay, a diagonal means it's identity matrix. So sigma square into I. So the point is actually we assume that we have only elements in the main diagonal of the covariance matrix. Okay, so that means see the covariance of maybe x1 with x2, x3, etc. They are actually zero, because we are assuming that case one is where features are statistically independent. That is one case. So that means we have only elements in the main diagonal. And we again, one more assumption that we make is, okay, specific cases each feature has the same variance. Okay, so that variance is actually the sigma square. Okay, so that is a case. So that we are assuming that a special case where the covariance matrix is equal to sigma square diagonal, okay, sigma square I. Okay, so if we make such an assumption, and we are considering that specific case, then we look into this g of x equation that is given. Okay, so then we can say that if we look into that particular assumption, we can have the maybe the third term, that is d by 2 into ln of, okay, 2 pi, and we have 1 by 2 into ln of sigma I. So these are going to be maybe say constants, okay, because d is anyway going to be constant for all I values, okay. And similarly sigma I is also going to be same, okay, for all I, because the sigma I is actually sigma square into the diagonal, okay, or the identity matrix. So that means we can actually disregard or ignore the second and third term in this particular equation, so that we can have g of x defined, okay, like this. That means we have as shown in the rectangle, that is x minus mu, okay, the whole square divided by 2 sigma square, okay, plus, okay, ln of maybe say natural logarithm of say prior probability. So that is a way we can actually maybe rearrange the term, okay. And so that is where x minus mu the whole square is actually, okay, is defined as x minus mu I transpose into x minus mu I. So that is actually just rearranging this particular equation, okay, and substituting. We know that sigma I, okay, in the g of x equation, we know that sigma I is equal to sigma square. So that is actually substituted there, and we will get the equation that is given in the rectangle. Okay, so that is a simplification maybe in this particular case. Okay, so that is the case. I think we will stop with that today, and we will continue, okay, in the next class. Okay, so that is for the time being. Okay, so thank you for listening. We'll continue tomorrow.